All right, good morning, everyone, on this sunny but chilly winter morning. Welcome to Saturday Morning Physics, to those here on the UM campus and to those watching our live stream. I'm physics professor Christine A. Dulla, one of the organizers of Saturday Morning Physics, along with our team, including Professor Tim Chupp, Carol Raybuck, Monica Wood, and the staff of the Warren M. Smith Demo Lab, Nick Arnold, and Sean Riley. Before moving on to our program, I want to remind you that Saturday Morning Physics is made possible by you, by your many generous contributions as Saturday Morning Physics fans. For more about supporting Saturday Morning Physics, go to saturdaymorningphysics.org. Saturday Morning Physics is also grateful to have the support of the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, the Van Loo Family Endowment, and the Pulikeshi Dayalu Astrophysics Fund. Before moving on, I want to note that today's event will conclude with the traditional Saturday Morning Physics Q&A. For those joining us online, please send your questions to physics@umich.edu. Just a couple upcoming events that we have. Our next Saturday Morning Physics will be February 28th with Juliet Becker from the Wisconsin Center for Origins Research at the University of Wisconsin-Madison. She'll be talking about surviving the death of a star, life on planets orbiting white dwarfs. And not part of the Saturday Morning Physics program, but another public lecture hosted by the Physics Department will be the Ford Distinguished Lecture in Physics by Dr. Richard Friend, Professor of Physics from the University of Cambridge. That will be on March 11th. And we just realized the date is missing, so you can note that down or check the website, March 11th for the Ford Distinguished Lecture. This brings me to our program. Our speaker today is Professor Finn Larsen from the Physics Department here at U of M. He'll be talking about an introduction to quantum computing. He was born in the Faroe Islands, an autonomous region of the Kingdom of Denmark, grew up on the mainland, but as a teenager spent summers in the North Atlantic working in the fishing industry, both on land and at sea, also engaged in traditional indigenous culture, such as the hunting of whales, which I confess I did not know before today.
I was asked for something that was not widely known.
He received his undergraduate degree from the University of Aarhus, doing some research at the Niels Bohr Institute in Copenhagen. He moved to the US for his PhD in physics at Princeton and joined the faculty here at the University of Michigan in 2001. His research over the past decades has focused on the quantum physics of black holes and other aspects of quantum gravity. And in recent years, his interests have expanded to quantum information, which is what he'll be talking more about today. Please welcome Professor Finn Larsen.
Thanks, Christine, and thanks everybody for coming on such a cold day. So I'll dive straight into it. This is a talk about quantum computing. It's a somewhat challenging subject to present. I have decided to go for three parts. First, what is it all about? What is quantum and what is computing? So that's sort of what's the central part. And then I will come to, well, what might it be good for? And, well, can we build it? Have we built it? When will we build it? And how do we do that? So those are the three parts. And the third part will explain why a quantum computer looks like a spaceship. So let me start with what is computing. The ordinary computing, the thing you have on a desktop, on a laptop, is digital. Digital computers are at the fundamentals level binary. They're all built on something that is one thing or another. Traditionally, people call it a 0 or a 1. What that means is that if you want to build a computer, you need a physical realization of pretty much anything that has exactly two settings. A light bulb that is on or off, a button that is on or off, an arrow that is up or down, something that is, well, binary. It can do two things, and exactly two things. That's how you realize a digital computer. So a quantum computer is different. Yes, it often brings up cats. It's because Schrödinger realized that cats, they have a famous binary property. They're either alive or dead. And it's binary. The aliveness is one or the other. But a quantum cat is more complicated. There's a range of possibilities. I asked the demo lab if we could demonstrate, but the cats didn't cooperate. So this is an example. It's probably the most famous example. It's not really a great example because, well, there are better combinations. There are better analogies. The best, I think, is that of a coin. A coin that really has two sides, heads and tail. But imagine that it is spinning. A spinning coin, as long as it's spinning, well, it's kind of indeterminate. It's not just that it's heads and tail, or heads or tail. It's really neither. As long as it's actually spinning, it's not both, it's different. That's what quantum is. It is true that if you stop it from spinning, it will become heads or tail, one or the other. Similarly, the cats, they really are dead or alive. It's just that you may not know. So that's a good analogy. It does capture some things well and some things not so well. One thing is that it is, in fact, still binary. Even as it's spinning, it has a clear oppositeness in it. Heads and tail, they are, in fact, opposite. Another analogy that's a little bit better, or at least captures a different aspect, is if you have an arrow that can point in many directions. Well, whatever direction it points, there's an opposite direction. It's binary. If you have a direction, you have the opposite direction. But here, there's a continuous set of directions. So it's not just heads or tail, it's kind of different directions, but whatever it is the opposite direction. That captures kind of a different aspect of quantum. Namely, that it's kind of continuous. It's not a button that's just on or off. It's kind of a whole set of directions. The settings here is, well, the bit is kind of 0 or 1. You might say that is north or south pole. Well, a qubit, the quantum bit, the fundamental thing that we build a quantum computer from, is more like a sphere, the surface of the sphere. And you can think about it as there being kind of an arrow anywhere on the sphere. Wherever it is, there's an opposite arrow. And it's continuous. It kind of means that if it was near the North Pole, then probably the qubit is 0. But if it's somewhere in the middle, it might be 50-50 or probably 1 or something like that. So it's not exactly 50-50. It has a continuous set of possibilities. And yet, there's something that is binary. There's something that is either it's on or it's off. These are aspects of quantum that are important for understanding quantum and how it really works. I could go on and have more analogies, but I've decided that this really is enough about the building block, the bit, the qubit. There are a couple of aspects here that I brought up, and they're correct, and they're important parts of understanding quantum. You know, a single qubit has continuously many settings. That's good. On the other hand, humans have known this since they invented the wheel, so it's not exactly profound. It's also true that qubits are probabilistic. This is a feature. It's not so clear why that's a good thing, because if you want to build a computer, I really want the right answer, not just some answer. So this could, in fact, come in unhandy, and it does, the uncertainty. It's one of your challenges. But what is the opportunity? Why is it that quantum computing has unique features that make it great for computing? Well, that's really because of a different thing. It's what is called quantum entanglement. So it's what I want to try to explain a bit more so than actually the qubit by itself, the kind of building block. So what is entanglement? Well, this is another aspect, like the qubit itself, where quantum really is different. In an ordinary computer, classical data, whatever you have, is encoded in individual bits, the 0 or 1. There's usually a whole string of them. There are many of them. But clearly, whatever you're trying to express inside your computer is one particular bit string. Quantum data is completely different in that it's collective. It's not a set of individual bits. In fact, no single quantum bit like this encodes terribly much. It's just up or down. However, it's a collective. No single qubit has a lot, but the in-between part counts as well. It really should be seen as a pair of qubits, not one and another, but, well, a couple. That is what entanglement is about, and is where the power comes from. So what you should think about is a community. You know, the University of Michigan. It's much more than the sum of its parts. There are certainly unique individuals. That's wonderful. Each is very much an individual, but there's also a community. You know, if you think about Facebook or some such thing, each person is unique and interesting. That's all good. It's an individual. But the really important part is that they have friends. And the friends even themselves come in different strengths. There's near family, there's, you know, very distant acquaintances, there's connections. So if you think about not how you could position the individuals, but how many networks could you make? How many connections could you make of different kinds? Even a relatively modest-sized network, it has much more richness than just there's a person or there's not a person or some other binary thing. There is, well, a connection. So the network is the aggregate of all connections via friends and friends of friends. And that's what gives you a better analogy for what quantum entanglement is that it's a social thing. It's the community that has a property that is not sitting in any individual. It really is only meaningful to discuss it as a combination, as something that's collective, that people have together. That's how quantum information is encoded. It's encoded in the entire network. So the quantum network is a thing where the entanglement resides in relations between the qubits. It's not just what are the qubits. They are themselves quite interesting, and I tried to explain a little bit about them. But what are their relations? Here you have a classical computer, a rather small one. There are 16 entries, and either one of them is either 0 or 1. And you could easily come up with different settings with a different combination of zeros and ones. What about the quantum computer? Well, it has these two quantum aspects. One is that it's like a qubit. So actually, each of these sites is not really 0 or 1. It's a bit of both. And therefore, you can think about the entire network as being not a single sequence of zeros and ones, it's all of them. All of them are there at the same time. So it's a much more complicated setting. They're all there simultaneously. And not only that, they're not just individual settings, they are combinations. If you look at each dancer, well, maybe they spin to the left, maybe they spin to the right, maybe they do something more interesting. But really, you shouldn't look at the individual dancer. You should look at the choreography. The collective is so much more than its parts. So the options for overall choreography in this kind of set, it increases greatly if you add even just one more dancer. On the other hand, you could lose a lot if you remove just one of them. It's the collective that really has the power here. It's a dance company. So quantum entanglement, the second property that goes beyond what the individuals do, and the one that really is due to that gives the power of the quantum computer, is the collective. The quantum entanglement resides in some kind of correlations between the qubits, the same way that a dance company is not really just several dancers. It does something together. So let's see how that works in an ordinary computer. In an ordinary computer, a single piece of binary data is called a bit, and I mentioned it's 0 or 1. And how do you build up a lot of information? Well, you first try to find out what symbols are. You, by convention, have symbols. It's called a byte. It has 8 bits. And then some examples might be a capital M here. It's a particular combination of zeros and ones. That's the capital M. Different combination, lowercase m. Different combination, a number. And there's a variety of different symbols that you can put in. But if you want to express something like Michigan, it's not that complicated a thought. It's just the name in capital letters. But, well, this is the 24-bit sequence that you need to express just Michigan. If you want to express pretty much anything in an ordinary computer, you need a lot of bits. Right. Whole book, lots and lots of bits. Each of them very simple, but you're many. Well, how does classical versus quantum information work? Well, modern technology, it has a lot of zeros and ones. So the physical realization requires a lot of little switches inside a piece of silicon. And it really is a humongous number. This little thing here, less than $10 on Amazon, 32 billion individual switches that you can put on either as 0 or 1. It's amazing technology, but it's built on the 0 and 1. What about the quantum equivalent? Well, here we have a pretty primitive quantum setup. There are 35. Each of these are individual atoms, and I'll tell you a little bit more about them later. But for now, each of them are qubits. So each of them can have this on and offness, but a little bit in between, kind of like our coin. But on top, it's a network. It's not 35 individuals. They really are sort of tied together in a quantum way. That you don't see with the eyes, but that's what's happening. They have quantum entanglement in them. You can think about it perhaps as each of them shaking a little bit, but they shake in a pattern. And that pattern has quantum information, and it's the full pattern that has many options. There are many, many different patterns, and in fact, this has, as it happens, pretty much the same amount of information as the 32 billion settings. So this is what should get you greedy and saying, you know what, I think quantum computing might get somewhere. This could just scale up pretty powerfully. All right, there's some options here. Of course, we're not set. What was this whole deal with probability and can we build it and so on? But this is the promise. There's a lot of different patterns. And quantum information is much, much richer, more interesting than the classical information. Classical meaning the normal stuff. So that was kind of my first part. Quantum is, well, different. Think not in your usual way. You have to think broader, you have to think differently. And that opens up new opportunities, and it's interesting, even just intellectually. There might also be applications of this, right? So that's where we're at. So what's the next part? Well, how do we get to exploit this? Well, how do we compute? How do we compute? Well, the way computing works is that, well, you have these sequences of zeros and ones, and, well, they are what they are, but then the computation involves flipping some of them. If it was a 0, it becomes a 1. If it was a 1, it becomes a 0. And you have some set of instructions for which ones should you flip and why. It's called a program. Some rules that some of these, they get flipped, and then you have an output that hopefully is interesting. It's how an ordinary computer works at its fundamental level. It has a sequence of zeros and ones. It has a program that says how should you change them according to some rules. And then after they've been changed many, many times, because it takes many steps to get a useful task, but still, fundamentally, it was just a bunch of flips. Many, many times to do something useful. That's what the computer does. What about quantum computation? Well, this is where you can do a bit better. Because if you do operations of just a few sites, it changed the whole story. If you have your network, and you imagine even a single site flips all of its friends to enemies, and vice versa, the entire network is different. It changes everything. Even though it was just a single place that sort of changed something. But what happened was completely different. So this is where the computation, because it happens at the level of the network, instead of at the level of the individual ones, the individual qubits, it has a lot more power. And this is where you really get some opportunity here, that it may take a lot fewer steps to do something interesting. Because your setting, your quantum information, is by itself more composite, more complex. Your computation, in a way, could become easier. It could also become harder. You have to control it. So the opportunities here. But that's the idea, that because the quantum information is set up differently, you have opportunities for quantum. So quantum computers are not really faster. In fact, they might well be slower. But they're different. They think differently. So the rule of the game is that you want to find some things that quantum finds easy. It turns out that things that can be done on an ordinary computer can also be done on a quantum computer. Now, that's assuming rather generously that your quantum technology has become as advanced as your classical technology. And, well, you've got a 70-year head start, so it's not really fair. But still, generally, the thinking is what you can do on a classical computer can be done on a quantum computer, but why would you? Classical computers are quite good. However, there are some problems that are a lot faster on a quantum computer. A lot. They really can be easy to do rather than difficult. So those are the problems that we want, that are quantum easy, but not classically easy. These are problems that have quantum advantage. The quantum way of formulating the problem is just better than the classical way. So those are the kind of problems we really want. Of course, there are also problems that, look, they're just hard. And the quantum computer, sorry, it's really hard. In fact, it's as hard as it would have been otherwise. You'd get no quantum advantage. So some things you can do, some things you can't. What research would like to do, research sort of on the theoretical side, would be to try to find things that are better on the quantum computer than on the classical computer. So let's take an example. What kind of computation might we wish to do? So let's try to take an integer, and I'm asking, please do write it as a product of two integers, of two primes, actually. So that's pretty easy for a small integer. I ask 21 and say, okay, write as a product of two integers. And you think a little bit, not too much, I hope. 7 times 3. It gets harder, though, if I say, well, how about a larger integer? Well, why is it harder? Because you kind of have to think through more options. And for each of those options, you actually have to multiply some bigger numbers. So, this would be hard. This is the answer. You probably could figure out certainly how to go the other way, like multiplying these numbers and check that it is true. But to find it, you have to do quite a lot of checking. Never mind, a computer can do it easily. But now, what if you do huge integers? Finding prime factors becomes difficult, and it becomes more difficult. In fact, so difficult it is pretty much impossible, even on a computer. Think, 100 digits. All right? Oh, I'm telling you, it's a product of two primes. Get cracking. And I'm sure it's just on your tip of your thumbs, but, tips of your lips, but not so easy, all right? It was 100 digits. So now think 1,000. This is hard. And why is it hard? Because you have to try many, many options. And for each of them, you have to do quite a bit of work to multiply them together, but computers are pretty good at that. It can easily multiply numbers like this that have 50 digits, multiply them together. Going from right to left, not a problem. But figuring it out by trying all of them, big problem. Well, it turns out that finding prime factors is one of the things that is easy on a quantum computer. You can do it. You can do it very easily. So it's one of the problems that have quantum advantage. And why would that be? Well, roughly, because it can have all the possibilities at the same go. You know that this is a product of two prime numbers. So you should just multiply them, except you don't know which ones. Let's try all of them. And if you do that on a classical computer, you pick two, and you multiply, and you almost certainly got it wrong. Almost certainly got it wrong, unless you were very, very lucky. On the quantum computer, you pick all of them, and you get all the answers. So, well, have you made progress? Yes, because you're a little bit right. And then you go back and say, could you make me a little bit more right? And a bit more right. And it doesn't take very many iterations before you got it straight. Just got it. This is why it's easier. It's because it can try all at the same time. It's simply different. You can try all. So that's one of the things that have quantum advantage. Right. Now, this is just an example that's sort of simple to understand because it's primes. It's just numbers. It's sort of algebra. Right. But okay, that sounds a little bit abstract and whatever. Actually, not really. Even prime numbers have practical applications. Modern encryption is based on some math problems that are difficult, kind of like multiplying numbers, but not multiplying numbers, finding the prime factors. And literally, that is what is called RSA encryption is based on. If you are really good at finding prime factors, like for big numbers, like 1,000 digits, if you can find the prime factors, you can find the code words. You can find a way in and breaking the encryption. This is what financial transactions like ordinary credit cards over the internet is based on. It encrypts and encrypts this way by basically multiplying by some big prime numbers that the adversary doesn't know, but if the adversary could find it out, could just find your credit card number, with security codes and all. Not good. So this is something that could undermine security in financial transactions like credit card payments. So this is what is called RSA security. I believe it's at least half of all transactions that are done this way. So these are applications of quantum computing. Right? You can see it was just a mathematical problem, finding prime factors. But are there others that have quantum advantage? Yeah, well, there are quite a few, but here are some. There's this cryptography business, so basically encryption. Right? Well, the credit cards, well, you're concerned, but the serious people, in government, they're not concerned. They're concerned that their military-grade stuff gets broken, so their secrets get out. And they're greedy. They would really like to break, the encryption of the adversary. So they would like to break high-grade encryption. And the estimate is that that would take about 6,000 qubits. It's quite a lot, but it's not astronomical. It doesn't seem impossible, right? This is why we have various guys with sunglasses going around the corridors and peeking into the labs to see how close are you, because they're concerned and they're greedy. But there are also other things you could do. For example, we'd like to simulate complicated molecules. There's a particular molecules, FemoCo. It's part of an enzyme. It can be used to produce some proteins. And it turns out that this particular molecule is actually really, really hard to simulate, to understand actually why does it even work? Why does it produce this protein. And in fact, it's even relatively hard to synthesize, apparently. So couldn't you just sort of analyze it on a computer? Well, it turns out that it's just too hard. Even though it doesn't look that hard, but it is. There are many, many options, and each of these atoms have quite a lot of electrons, and it's just complicated. But on a quantum computer, about 200 qubits should do the job. We're getting closer. For some physics applications like superconductivity, these are amazing materials that don't have any resistance to current, and they have this very special two-dimensional kind of pattern. But still, there's a lot of things going on here, a lot of entanglement between the various atoms. Couldn't you please simulate it on a computer? Not an ordinary one. It's completely out of reach. But 100 qubits should be able to do it. So it's the sort of thing where we say, well, maybe soon we can actually do this and get help with some scientific problem that is practical in a way, that we don't know how to do yet, but we could soon. In practice, what we do is hybrid computing, or at least envision to do, is quantum computing that is hybrid. So ordinary computers, they're highly optimized, they have many years of development, they're relatively cheap. Maybe you don't think your laptop is cheap, but there's a lot of little things going on in there. The best strategy then, and certainly what is envisioned for the foreseeable time, is not that you exchange your iPhone for a quantum iPhone, a Q phone. It's that you do both. That you have some hybrid computer. That you have a traditional computer over here that does what it's doing well, which includes preparing your problem in a form that's really good for quantum advantage. And then it sends it over to the quantum computer that does its thing, sends it back, and it probably needs some processing. It may not give the answer, but it gives the essential part. And then the ordinary computer can figure it out. Maybe it's going to take several changes back and forth, but that's what the hybrid idea is about, and that's what seems realistic within the foreseeable future. Hybrid computing, a bit of classical, a bit of quantum. So that was the computation part. I can see this goes a lot faster than I thought, so you're going to have so many questions afterwards, I hope. Could have stuffed more in. All my extra slides I cut out. They should have been there. But anyway, second part. Again, I'm trying to get across, using somebody who's much better at words than me, with quantum is different. And quantum computing is not just, couldn't we improve our little switches on the silicon and make it smaller and smaller? Well, there are people who work on that in ordinary computers. But quantum computing is different. It's simply thinking differently, and that means that for certain things, you can get huge advantage. And that's just interesting. And it could be really important, right? If only we could build the things. So, where are we? Well, the key question that you first should ask is, how do we realize a qubit physically? Right? It was not obvious how you should realize a bit physically, like these little switches. In the early days, they literally had light bulbs that were either on or off. They were binary. Right? They also broke, so there were some technological issues. But logically, they were just something that was on or off, and then it was figured out that these switches on silicon, these diodes, in fact, are really good at this. Either there's a current or there's not a current, and this you can miniaturize enormously, very good. But what do we do with quantum computing? Well, invent a qubit. And like your classical bit, which has many options, and it's not completely obvious which one is the most advantageous to miniaturize and make reliable and so on, for the quantum bit, the qubit, it's not obvious either. How should I do it? All right, how do we realize it? Oh, and then once you have committed yourself to how to realize it, and as you do that, you should probably think ahead that, well, how do I enter quantum data? How do I make it entangled? And how do I manipulate it to go from one entanglement pattern to a different entanglement pattern in a very predictable way where absolutely nothing is lost? Because the problem in part with the community is that if you lose just a little bit, you lost everything. It sits everywhere. So you really can't miss anything. In that sense, it's very fickle. But anyway, when you've done your thing, manipulated them, retrieve your output. And each of these steps here are, technologically speaking, different. And different technologies are good at different things. Some are good at something, some are good at something else. The real technology should be good at everything. So how do we realize our qubits? Well, there are sort of 6 to 8 different technologies being pursued, thought about. Here are 3. There is the array that I gave you earlier, 35 different atoms. These are atoms that are ions. It means that they actually have an electron that was lost, so they have charge. Usually atoms are neutral, equally many electrons and protons in the nucleus. These have charge. That's good, because that means that you can trap them using electrical fields. They respond to electrical fields. Charge is repelling and attracting, depending on whether other charges are positive or negative. So you can trap them, and that is what has happened here. They've been trapped because of some electrical field that you don't see. They sit there. And they sit there quite reliably. It turns out that it's a bit hard to entangle them and manipulate them. They're really good at keeping trapped. That's a very good technology, but the entanglement and the manipulation is one of the weaker things in this setup. You need to control the entire pattern reliably. And you know, some of them are a bit further away than others. So, you know, just practical stuff, but you know, some are closer, some are further away, and you want them all to be entangled. Not so easy. And it turns out that this is about as big as it comes. That if you want more qubits than this, you need different arrays, each of them with 30 odd. And then you need to combine those. And, well, that's your problem. So you have a technology that works for some things, but not so well for other things. The superconducting qubit is this one. There are only 7 of them. This here, there are 7 of them. These are some wires that goes in to help controlling them. But each of these qubits by themselves is basically 1 qubit. So there are only 7 of them here. But this is using a different technology. I'll tell you a little bit more about it shortly. And this is a silicon qubit. This is trying to say, well, we're really, really good at ordinary qubits. Ordinary bits. Couldn't we somehow pack them? Yeah, you know, Intel is working on it. And, well, here there's only 4, but one can do bigger arrays. But this is research style. A relatively small number. How good can we be at entangle them, at manipulating them, improving them, building them, constructing them, the actual manufacturing? And there are other technologies. You'll see one more. All right, so one of them, the superconducting quantum computer, is the one I do want to highlight. It's actually, in a way, the most complicated one to understand what superconductivity really is. But, well, in short, it's a state of matter where there's no resistance, which means current can go and go and go and go. You don't actually need like a voltage or something. It just keeps going. You know, you don't need to sort of keep pumping it. Superconducting has no resistance. It just goes. So the physical qubit in this case, there are several different sub-technologies on superconducting qubits, but one of them is simply to have a little loop and say, oh, the current keeps going, that's wonderful. Go, go, go. But which direction, left or right? Or a little bit of both? And how is it entangled, by the way, with the other ones? So that's the setup in the superconducting qubit. And the kicker there, and the reason I really have to mention it, is that it must be cold, really cold. And we're not talking Michigan winter kind of cold, you know, really, really cold, right? So Michigan winter is up here somewhere. It's basically room temperature. But then you need to freeze it down. You need to freeze it down more and more and more, and you get awfully close to 0. And the hard work, one of the aspects of hard work, is that, well, it must be so cold so you don't lose any quantum entanglement. And the hard work in part is that, yeah, but I need to get information in and out here to control things without messing them up. So that's why you get this layered structure that you see on the view graphs generated by AI. No, they were not my own beautiful creations. So it must be cold. And the little chip I showed you with 7 guys sit down here. Right. There are some that are superconducting qubits that have about 100, 150. I just couldn't find a picture of them. They just write news releases, but with the picture, that looks like a spaceship. And they all look like that. If it's bigger, well, it still looks like a spaceship. But it's really how many do you have in the bottom, and how good are you at reliably manipulating them? Right. That's the hard part. So, well, where are we at? Well, one key question, I guess, is how many? I want many. Okay, good. Well, I looked at the internet and found that the current record seems to be 6,100. A Caltech setup, these are neutral atoms. So they do not actually have any charges, so you need a different technology to manipulate them. But that technology is sort of well understood, and you can do many. That's the advantage of this. You can do many. And can you entangle them, though? Can you manipulate them? Not quite as good. Not quite as good. So this may not be the right technology, but, it's very interesting. There are many of them. But your big challenge really is, are they reliable? Can you, entangle them? Can you manipulate them? Do they, in fact, even if you give them some quantum entanglement pattern, does it stay? Or does it accidentally somehow communicate a bit with the environment outside? And that means that the whole pattern, the collective stuff, gets out of the fridge and it ruins it. No good. No good. So can you do that? Can you maintain it? All right? And that's where, well, some people are yay-sayers or some are naysayers. Maybe it's progress, maybe it's not. That's how research works. That you tried individual pieces. And one of the pieces would be, please keep the quantum state for as long as you possibly can. And with some of the technologies, you can do that for seconds or even minutes. And that can give you a lot of manipulations. That's enough for a computer to do quite a lot. Unfortunately, there might be other technologies that are more reliable. So what should you do? It's not just maintaining it, it's computing. Oh, and you noticed, somehow, this is always how a quantum computer looks. If you Google image, AI, this is how it looks. Just, golden, Trump style. So this is the biggest challenge. The biggest challenge are errors. Mistakes happen. It happens also in ordinary computers, that sometimes the bits actually flip accidentally. You need a bit of protection from that. That has to be designed in. But quantum technology is much more challenging. For one thing, it didn't have those 70 years of improving, but it's also just fundamentally speaking more challenging. When you have something that's not digital, the whole point of digital is that it kind of is robust. Either it's 0 or it's 1, and they don't look alike at all. But when things are sort of continuous, they could be a little bit wrong. And then later, they could be a little bit more wrong, and then it could kind of slowly get more and more wrong until you completely lost it. It's more challenging. And there's this whole thing about, it sits in the pattern. It's collective. It's a network effect. If you don't have control over the network effect, if you only understand the individual little qubits, not good enough. Single error can be fatal. So you need redundancy. You need, one thing is to estimate how many qubits do you need to sort of theoretically have enough information in there that I can do my problem. Yeah, but once you build it, you're just going to have redundancy. You're going to have more qubits, so that in a way the information, after all, sits multiple places simultaneously. It's simply redundant. And that means if something fails, you might still recover. That's the key challenge to why haven't we built it? Why did these 6,100, why aren't they good enough? Well, because too many errors. Too many errors. You can't entangle them reliably, you can't keep it. So when I look back and say, oh, I was promising you that you could do all this stuff with not that many qubits, really, 100, 200, and then I showed you 6,000, all right? Well, I was not entirely honest. These were the perfect qubits. But if you estimate how many realistic qubits with sufficient amounts of redundancy that it will work, because every time you make an error, you can kind of test for, is this pattern of qubits even a good one? Is it even a legit one? Oh, it's not a legit one, but I can recognize how it has become a little bit illegitimate and fix it by only allowing some patterns and being able to check that those entanglement patterns are in fact good enough. These are among the legit ones, these are among the illegitimate ones. Illegitimate, hopefully not terribly legitimate, just a little bit, so that you know that, oh, this is what it should have been, and you can fix it. But that redundancy is expensive. It's expensive, and it gets more expensive the more qubits you have. You need more redundancy. So this is more realistic. 100,000, each of which, 99.9% reliable, maybe even 99.99. But that's realistic. The perfect, well, that's 100%, and it's not going to happen, all right? So this is where we're at. We can sort of imagine things, but can we build it? No. No. But it's not necessarily too far off, all right? So what we want is what's called fault-tolerant quantum computing. What we have is called NISQ. Beautiful word. No. But anyway, it stands for noisy, intermediate scale quantum computing. So a few hundred qubits maybe, but imperfect, they're noisy. They sometimes, just change in ways you didn't want. They were not part of your instructions. They were part of just, stuff happens. So where are we at? Well, quantum advantage has been demonstrated. Some problems that are nearly impossible to do on a classical computer, on an ordinary computer, can be done on an actual existing quantum computer. That's quantum advantage. It's been demonstrated. It cannot be done on any classical computer. Unfortunately, the problems that have been done are kind of problems that were specifically designed to be good on a quantum computer, that the quantum computer could do them. It was kind of like, do what you do, and let's call that the problem we wanted you to do. And then you did it really well, because that's what you do. And a classical computer couldn't do it well, so let's call it quantum advantage. Right. This was artificial. No fair. I want a commercial application. It doesn't have to be in every iPhone store, any Apple store. It has to be, could it solve one of my chemistry problems, one of my material science problems, maybe other problems. Those would be where I'd say, oh, now it counts, we improve from there. That's where we're not at. So what will happen in the next 5 years? Well, we will have progress. We'll have progress towards scalable quantum computing, fault-tolerant quantum computing. People have realized that we can correct errors. In that sense, it does work. But on these devices that have, 7 qubits. Could you scale it, please? Does it work? Let me get back to you. That's the sort of thing that's reasonable to say, yeah, that will happen kind of soon. That'll happen kind of soon. Quantum simulators that are not designed for a specific problem, but that in fact you can, massage a bit around and program a bit. Those are near-term goals. Let's try to solve problems like molecules in hybrid quantum computing, and let's do it in a way where we don't decide what molecule to do and then simply build the quantum computer for that. It should be something that is programmable. One of the side things that really aren't obvious is what's called quantum sensing. That's what this thing here is all about, this AI-generated thing. What it is a thing you might have thought was undesirable. As I told you, the quantum computer, you really, really want to keep it isolated. is really pesky that the environment keeps changing it in undesirable ways. It's so sensitive. But you can also turn that around and saying, did you tell me that your device was really sensitive to the environment? Doesn't that mean that you can measure things on the environment really well? It does. That's what's called quantum sensing. One of the things that if you're a quantum computing person, you would say, oh, that's really undesirable. Please stop doing that. But if you do quantum sensing, you say, oh, that's nice. I can measure a magnetic field that's a billionth of the size of the magnetic field of the Earth. Oh, couldn't that mean that I could start imaging Earth without actually having to drill down and finding my rare minerals? I could just take a picture of what it looks like, some kind of X-ray of Earth. It has to be really precise. That's the promise of quantum sensing. It's a side product. It's not what we wanted to do if you just think quantum computing, but it's what you think in part if you say quantum technology is quantum sensing. So these are things that will happen soon, are happening. Usable quantum sensors that you actually can use for commercial things. But first of all, from my thinking at least, this still really is in the realm of scientific exploration. We study quantum computers because it's interesting, right? And if you think really big picture, what is it that is interesting? Well, we have some traditional features, frontiers of physics, the smallest constituents of matter. Atoms, what are the atoms made out of? They're made of quarks and so on. Strings, obviously, I'm a string theorist. And we look for dark matter and so on. What is everything made out of? What are the smallest constituents of matter? How does it work? Oh, and what are the biggest? How does the universe work? How did it even start? These are great questions, and these are traditional frontiers of physics. Sometimes, at least among non-scientists, it's a little bit less appreciated that there's sort of a third frontier, complexity. If you take individual things, more is actually different. I tried to emphasize how a quantum community is just more than a sum of its parts. If you just understand the individual parts, you still haven't understood the community. You have to understand how do they build it up? How is it that more is just different? And that's a different directions from the finding the smallest, finding the very biggest. It's the how does it build up? So quantum computers, they don't think faster, right? They think differently. I've said it multiple times, but from a scientific point of view, that's kind of the point. That's the interesting scientific question. The different stuff, how? How does that work? In principle, how does it work in actual devices? How does it work in the lab in various contexts? Can we apply it? But also just, it's an interesting scientific question. How does quantum complexity work? And this is one of the themes of current research. How does quantum complexity really work in many different contexts? My own research actually is not directly on quantum computing. It is on quantum information, though. I'm interested in black holes. Sounds maybe like something that, yeah, it's in the universe, right? And clearly that's definitely what AI thought it was. But I did mention, yeah, quantum black holes, so it did something here that doesn't really show very much, but anyway, it's what it does, and it's pretty. And the point of the research is quantum information. These black holes, they're complex, but they're complex in a certain funny way. In a certain simple sense, black holes are the simplest objects that you can imagine out there, because they have sucked everything in. There's no structure there. Unlike a star or something that has all sorts of stuff in it, but the black hole has no structure. It does, however, have a lot of quantum structure. So what really is like, what happened to all that structure that was sucked in? Well, it's still there at the quantum level, except quantum entanglement. It's like, well, a quantum objects. And therefore, what I'm actually interested in is how does short distance simple entanglement between a few qubit-like things build up and become astronomically big in such a way that one can reasonably say that is what builds the entire black hole, is what builds the structure of space and time. So that's where my research sits. Quantum entanglement is what I started out with as my PhD thesis, and went on with how does it build up, big time, in quantum black holes. Oh, and back again. Actually, to really understand quantum entanglement, you really should look at things like quantum computers, quantum information, and so on, because this is how you really understand how more becomes different. So, that's all I have to say, but I do want to advertise that if you're interested in the black hole part, there is a public talk in a month by one of the masters of the field, so I should advertise that as well. Thank you for your attention.
All right, we'll take just a minute or two for those who need to head out before we go to our Q&A.
My student left. Yeah. So it was 10 minutes short. Do I get paid anyway? Oh, right. Welcome. What?
240,
Oh.
240 students.
Ah. The young ones. You say the young ones. I see there's a variety of students here at different levels. Different levels.
For those who are in the room to ask questions, we have a microphone set up over by me on the stairs here. And I remind those who are watching the live stream can send their questions to physics@umich.edu. All right, let's get started.
When you talk about a quantum easy problem, you're not saying they're not polynomial time problems, right?
They're polynomial.
They are well, like Shor's algorithm's not polynomial.
It is. It's n cubed. So
No,
you make
I thought it was 2 to the n. 2 to the n, 2 to the log of n.
classical. No. So it's n cubed. So yep. What the question is that so if you do a prime numbers and it's you say, oh, how about if I put 10 times as big, 10 times as many digits? Sounds a lot harder. It is, but it's only 1,000 times harder. It's n cubed. So.
In the room, and then we'll go online.
Thank you. Appreciate the lecture. I understood most of the words, so good job. On the error correction, I noticed it was 1,000 to 1 was the ratio that you had for on the very right side for 100 qubits, and I think it was a 5,000 to 1 at 200 qubits, and some number I couldn't do the math quickly in my head to the left of that. It's not linear. Can you help me understand intuitively what's happening there?
Yeah, so this was a little bit of a quantitative question. It was that these numbers I gave for if you needed more qubits, you needed more error correction. And I was illustrating that by saying how many physical qubits do you need, and it's being pointed out. But it did seem to increase the factor, but not sort of uniformly. How on earth did I get that? I got that by Googling different sources. And, there are different ways to estimate that. What's a realistic qubit anyway? And, sorry, the numbers were set differently. I was not using a uniform algorithm. I was trying to, what's a reasonable number to do realistic cryptography, or for that matter, realistic simulation of superconductors. And these were numbers that came up, and I did not overthink it, so sorry.
But the trend is that it seems to grow, yes?
Trend is that it's
so
harder.
Do you have any comment on the intuitive nature of it's some sort of three-dimensional aspect, and the network is becoming...
It's the network.
The network,
exactly.
Yeah.
That as you make the network bigger, then you don't need just, each qubit, what if I had a 10-time redundancy? Oh, that's not good enough. You need how many connections do you have? How much entanglement do you have? You need redundancy in that. And you actually also need, how many manipulations do I need? One thing is keeping it and keeping the entanglement pattern, but how many manipulations do I need? That's slightly different for each of these. So, you need to put in all of those and come with an estimate.
Thank you.
And
Move to a question online, also about error correction. With redundancy, and an error occurs somewhere, how can you tell which version is true?
yeah, no, I mean, that's exactly right. But you know how that works normally. The way it would work is that if you have a normal bit, 0 or 1, is that you might say, why don't I have 3? And then I make them all identical. And if there are 3 zeros, I really meant a single 0. If there are 3 1s, that's what I meant. It was 1. What happens if one of them flips? Well, clearly the pattern is wrong, because the pattern should be that they're all 3 the same. But since there are 2 zeros and 1 1, let me guess that the 0 was the correct. So in fact, let me flip the last one and make it 3 zeros again. I fixed my error by redundancy. Well, this you can do at the quantum level too. You can say, well, this entire entanglement pattern, is this legit? And you find, no, but nearly. Let me fix it back to a legitimate entanglement pattern. And that means probably I fixed my error. There might be a small chance that I even made it worse. But I've improved, and then I keep checking every now and then, is the entire network, it's in fact called the code word, is it in the right form? If it has not the right form, like all 3 being zeros or all 3 being 1s, you know something went wrong, and you have a clue as to what went wrong and how to fix it. That's what the thing is, and it's pretty amazing that that works at the quantum level. But that it does. It works very much, really well, elegantly at the theoretical level, and it's been proven to work in some smaller networks at the actual practical level.
Since you're talking about networks more, let me take another question online. Is entanglement a type of network? Would you really say that it's a type of network?
Yeah, so there I obviously use an analogy. And I would say the entanglement, well, sometimes it's being studied at the level of just, say, 2 qubits. And it is true that it is a network, it's collective in the sense that the entanglement cannot be assigned, absolutely not be assigned to this one or that one. They have it together, right? I mean, this is socialism for you, right? It does not exist individually. It's together. So in that sense, it's a network. Now, a network of 2 ones, that's not fair. But I'm illustrating this because for a computer, quantum computer, we really don't want just individual entanglement with a couple of pairs. I mean, that's very interesting scientifically, but it doesn't get us really anywhere. We want entanglement for the entire network. That's where we get a lot. So that's why I used the network. You could call it array, but the strongest entanglement would be if it literally was all-to-all between all my individual qubits. Right. May not be quite as powerful as that, my actual technology, which is why I need more.
Go to the room.
So when you were talking about the number of realistic qubits, that are needed to do something interesting, so it becomes really, really large. And for it to be fault tolerant, it sounds like you need really this network. So you need the connections between the large number of qubits. So given that, would you speculate as to which of the physical implementations could be most promising? Because in my mind, I imagine if I'm trying to connect a billion things together, if I have to actually solder wires between them, that's very hard, versus if I have neutral atoms that I just need to move closer to each other, it might be easier to create those virtual wires. Any thoughts on that?
Yeah, it's hard to speculate on that. I think the key here is that it might even be that different technologies are good for different things, right? That what you need to break into your worst enemy's, vault could be one thing, but what you need for simulate could be a different thing. So that's sort of the best way to hedge my bets. And that what I know for now is this thing that superconducting qubits are what is considered the best overall bet, that if you say, oh, but how good are you at maintaining them and manipulating them and reading them out together? They are sort of the best. But Okay, but what if I want to, have more? What if I want to have more reliable? Say, the ions, they are the longest. They last the longest. The readout is really poor for superconducting qubits, but they're easy to manipulate. They're reliable that way, or easy. They have advantages, different ones. So it's hard to know. It's also that different kind of technology, some has been developed for ordinary computers or for cell phones or whatever, so it's off the shelf. It's cheap, it's highly optimized, but it's almost cheating, because what about some of this other stuff that you're only creating now? That's going to be optimized too. But how much in 10 years? Well, I don't know. Right? It's going to be a lot better, but maybe some obstacle will come. So it's hard to speculate precisely. This is why I'd say this is frontier research. It's not really, there are companies doing it, right? IBM and IonQ and Google and whatever, they have, but they're not getting a profit soon.
We have a question online about ions in particular. Since the linear array of ions isn't so well suited for quantum computing, would a circular array of ions perform better?
So it is certainly a good idea to say, what are our architectures? And hey, why should it even be linear? Why don't we put them in a cube or some such thing? There it has to do with, for the ion specifically, well, you need these electric fields to keep them where they're at. And there it's sort of, it's a bit hard to make sure that you sort of push some inwards so they stay without actually messing up the other guys. And there, look, I'm not an expert on that, but I'm told that the array is sort of the way to build a trap, that's where you're good at it, and, doesn't work so well with other architectures. But some of the other technologies, you very much will pull not at linear. You might make them, you might make them even cubic or whatever, so it's just three-dimensional. And then somehow that seems like, then you're closer to the other guys, right? It should be better to build entanglement. On the other hand, you also have more ways to mess it up. So, again, this actually has to do with the application. There might be some applications where you are perfectly happy with having mostly nearby connections, and some others where you really, really want far-away connections.
Come back to the room.
Yes, I had a question regarding, all right. So there's a few different examples that you gave up there, and one of them was the network, and it seems like the larger the network, the better it could be at finding the answer, until perhaps it gets too big of a network. It only takes, which is introducing more chaos, right? Yep. So I guess my question then is and people are targeting maybe some smaller qubit focused problems, and then people are targeting some larger qubit focused problems like breaking security codes. So is there a point where is it better to build out a larger qubit computer, but you can manipulate them to turn it off for smaller problems?
I'd say that it's a little bit similar to a previous question, that it does have to do with what problem you're interested in. Most researchers, they're focusing on maybe not the full shebang, the full stack, but just, could I get qubits that last for a long time? Could I make qubits that I can manipulate reliably, or whatever? Not the full problem. And then maybe I could somehow connect these various technologies. And that might require multiple technologies. The array of ions, well, to connect them to others, you're using light that goes between different arrays. Light is also a good technology for quantum information. It's just really bad at making stand still. So therefore, well, you use it for communication. And why don't I study quantum communication? Yep, that's what some people do. Getting good at manipulating the photons while keeping the quantum information. So I'd say, how does that build up? Well, maybe multiple technologies? I don't know.
Very good, thank you.
two very unrelated questions. First one is simple thought. You talk about information processing in a network. We've got one of those in our heads. Is there any sense that quantum computing is used at a biological level?
There has been people who have said that, including very prominent ones, prominently Roger Penrose, got a Nobel Prize, so, that particular suggestion, I think, is basically widely been considered a quack suggestion, but then again, it was a Nobel laureate, so has there been suggestions? Yes. Let me say that they have not had high impact. People, you simply don't see it. I mean,
Okay.
It's true that, there's something similar, that obviously each neuron is something, but the collective does more. And how does that work? Interesting question in neuroscience. But is that a quantum type of connection? I believe the numbers just don't work out in what is the speeds, what are the scales, could these really be quantum correlated? No, it's not that kind of correlation.
Okay.
We think.
All right.
We being everybody except Penrose.
All right. Second question was, so I got your idea of the qubit with the arrows in different directions and lots of different representations. And I could think, okay, I could represent that in a classical way in a classical computer with a lot more bits, right? The entanglement of, one of those approximations to another one would be harder, and I don't know if we understand enough about entanglement to be able to even simulate two qubits in a classical
Oh, no, we
way.
understand that part. The rules are known.
Okay.
The thing is more just that to actually simulate it, there are just so many options, even for a relatively modest size molecule, quantum chemistry, not even of giant molecules. It's really hard because all of the things are, normally what physicists do is approximations. We take this into account because it's the most important. Then we do this, then we do this. But they all matter. There's so many electrons, and their mutual repulsions and whatever are kind of similar. So you just need to do it on the mark, and then you have your entanglement. So you need some quantum wave function that has everything. And you don't get to approximate anything. Writing down an algorithm that would do that on an ordinary computer is, in many ways, easy, done. It just wouldn't work so you have to then do shortcuts that are wrong. But that's what it takes to get an answer. And in many ways, that's sort of what quantum chemistry people do. They know what they should do on an ordinary computer, but they can't.
They can't get it.
So the art is, what do I try to do well, and what will I accept doing poorly?
Okay.
Yeah. No, so we understand what it should do, even for rather big systems.
Thank you.
Let's go online. How is space being explored or used to harness the cold environments needed for quantum computing?
Not that I'm aware of for the quantum computing itself, but one of the little pictures and applications was on space-based lasers. So basically trying to use quantum enhancement between different satellites and basically getting the distances between them right, not just 2, but even 3, and trying to see how the triangle can stay. And these things are good for quantum sensing. So it's used at least for, this is for gravity waves. It's being done, hopefully, within, not that many years. It's being built to use quantum sensing. And that is harnessing the cold for quantum phenomena. But I'm not aware of the quantum computing by itself, but maybe. It's probably not actually also, it's not really cold enough for some of these things. It's cold, but, it's colder than the Michigan winter, but it's not cold.
Another question online. How many years would you estimate, 2, 5, 10, ? Before quantum computers become commercially viable, and who will be the likely early adopter customers?
No, the early adopters is for scientific computation, I think. That's even the early computers, the digital computers, there are people who could, for example, custom build some computers to some applications and so on. This is the sort of thing we're looking at. But how many years? Well, for that, for the proposal, the answer is that definitely it'll be done within 5 years. And but the realistic thing is, well, some things will be improved by then. Quantum sensing is a thing, and it'll be better. And the computation, I don't know. For one thing, I'm not completely an expert on the technology there, but also I think there's a lot of estimates that are all over the place.
And will quantum computing impact the future of Bitcoin? Cryptocurrencies?
Yeah, I mean, it's not a completely silly question that Bitcoin is based on, you need to do really hard computation, and in order to basically, you can mine them, and that takes a lot of effort. Couldn't you quantum enhance that? And I believe for the actual kind of parallel processing you need for Bitcoins, I think the answer is no. But there are papers that say things like quantum AI and other things like that to do parallel processing for, things that, but to me it doesn't really add up. It's not the right, again, it's different. And there's some things different is good for, and there are others where it's not. And I don't see it.
Come back to the room.
Hello. So my question was just asked, which is, in your professional opinion, when we would have quantum computers? It will be within like decades, or this century, or next?
No. It's not. It's 5 or 10 years.
I mean,
it's 5 or 10 years. It's just that don't expect them to be universal quantum computers that you go and buy. It's more like, companies might have these things that they offer to companies mostly. It's going to be expensive, and then sending off your question to them for a subroutine. You have your own computer that sends off basically some kind of subroutine. You get your answer back, and you're like, oh, great! Now I can break the bank, or whatever, right? So, that it's a subroutine. You don't buy it. You have it as a cloud resource, right? And that, I think, you can get them now. It's just that they're not very good. And I'd say, but 5, 10 years for actual applications, I think is perfectly reasonable.
So this application would be the simulating the molecules and also...
Exactly. Simulating chemistry or other things. Chemistry or materials, scientific computation.
Next question in the room.
Hello. I generally know how entanglement works. If you have one particle here which spin up and you measure another one that's entangled to it, it'll be spin down most likely. The question is, if I'm able to change this one to spin down, will this one in your group of qubits automatically turn to spin up? And does quantum mechanics or quantum computing rely on the fact that it will to be able to work?
Yeah, so this is the smaller scale level of entanglement, which is also super interesting, especially to understanding the foundations of quantum computing, or quantum mechanics, I would say. In fact, in your example, it's not quite right that you would take, say, one that is up and one that is down, and you would sort of try to flip one of them. The situation is more like, one is up and one is down, you just don't know which one. And therefore, in fact, if you say, let me go flip them, nothing happens. You knew one was up and one was down, and you still know that. So that was not helpful. So it's the operation is more along the lines of, actually it's not quite true that one was a 0 and the other was a 1, or vice versa. It's more like it was a 0 minus 1, or maybe a 0 plus 1, and there are more options than just up or down.
But
that's your
my
manipulation.
question remains the same. It doesn't matter whether it's in between the 0 or the 1. If I have this one and I change it slightly, will this one change slightly? And is quantum computing dependent on that change happening?
I think you can do either. You can manipulate an individual one, turn it, without doing the other one. Or you can say, or you can do it, and that way you change the entire pattern a lot. But you can also do it as a collective. You can say that, well, this one over here, it's 0, 1. I don't really quite know what it is. But whichever it is, if it's 0, flip the other guy. Or don't flip the other guy. If it's 1, flip the other guy. If it's a bit 0 and 1, do the middle. Do the. So that's where quantum instructions are very different from ordinary ones that are sort of conditional. If you're 0, don't do it. If it's 1, do it. If you're here, bit of both, it's complicated.
My question started out almost identical to the last one of entangled particles, like spin up and down. When you talk about multiple qubits, are you talking about more than 2 particles being entangled, or are you talking about just pairs of multiple entangled pairs?
No, absolutely more than 2.
More than 2?
Multiple entanglement is massive entanglement.
So 3 or more particles entangled together in one?
Absolutely.
Okay.
So therefore, it really is becoming a community.
Yeah.
That it's all-to-all entanglement, at least at the middle of the quantum computation. It's all-to-all entanglement. And that is
all
also...
of them are entangled in one community?
Yeah, all one community.
Yeah.
And
Okay.
there's none of them you can say, oh, tell me what the state of this one is, or the state of that one. Oh, I can't tell you.
Yeah.
It's completely meaningless, whatever I tell you, unless I tell you what all the other guys are.
Yeah. Okay.
And so there you go. I must tell you everything, or you have nothing.
Okay, thank you. Previously, I thought they were talking about just a bunch of pairs of entangled.
I mean, of course, that's something. And of course, in the architecture, you might be really good at doing nearby entanglement,
Yeah.
and not so good practically at doing all-to-all. But in theory, to get the maximal performance, you need complete entanglement.
Yeah.
That's, again, another reason that, there's realistic and there's
Okay, thank you.
what you actually can do.
Let's take a question online. Since different quantum technologies are good for different things, has there been any work combining multiple technologies into a single hardware stack? For instance, using neutral atoms as memory storage, then writing the data to superconducting qubits for manipulation.
Yeah, on that, so I'd say yes, there definitely is. I mean, I mentioned how photonics, photon qubits, are kind of good for perhaps tying different arrays of ions together. That's the one technology I'm aware of. Again, also using photons as kind of a quantum internet. You can actually send entanglement from North Campus to Central. And, that's an interesting thing to do, to just check, can I do it? And, but of course, can this send a lot? No. But let's try to get better. So that's all I can say really on combining them. But when the question was, has there been thoughts on combining them? Absolutely. Is this going to be the way to go? Don't know.
Come back to the room.
So classical computing has gates, like AND gates, OR gates, NOT gates.
I don't quite understand. Fast?
So classical computers have gates, like AND gates or OR gates.
Yes.
Yeah, so I'm wondering, what's the quantum equivalent for
What are the quantum gates like? Yeah,
what's
so
the simplest operation?
They are some of the same operations that you're familiar with. The NOT operation takes a 0 to a 1 and a 1 to a 0. The quantum NOT works exactly that way. It's just that it's like your arrow. I say that, yeah, but your arrow is not either up or down. But the NOT operation says take arrow in one direction to exactly the opposite. So there. That was the simplest one, because that's a 1-bit operation. It's more interesting to have some that have to do with multiple bits, the logical things, and you have 2-qubit operations as one of your basic logical quantum operations. And it's very similar, I think I said it very quickly just before, to a controlled NOT. A 0, do nothing to the other guy. If it's 1, flip the other guy. But that gets much more complicated. That's called an XOR, I think, or something like that. And if this was classical, but it's not. Once these are superpositions, this becomes really magical. It becomes a collective thing. It doesn't take terribly complicated logical operations. This is why this is not that hard to learn in a class. These basic logical operations are in lecture 3. And you need to build them up to factor prime numbers, but but these are somewhat simple logical operations, very simple logical operations. It's just quantum superposition gets in the way.
Okay, next question in the room.
If the modern computers now are coming up and giving hypothesized, or their basic computers are lying and making up stories, will the new quantum computers, how can you trust the new quantum computers?
Well, I mean, so this is highly relevant for AI, but I do think that most of the problems, a big class of problems that we're interested in are actually problems where you can validate, right? If you have the prime numbers, the hard part was finding out what the prime factors are. But if I tell you what they are, for you to validate that they are in fact giving the product that you asked for, it's easy. The hard part was finding which prime factors will give that product. So a large class of problems are of that kind, NP hard in ordinary computer language. Here they are QNP, but it's related, that you can validate. Of course, there are other problems where you can't.
Also, when you're reading about AI, it says you can spot AI because of the bad spelling. Now, why would you have bad spelling if AI came up with it?
I'm not an AI expert, but so that's an excellent question.
Why
I also think
AI
that you can
have bad spelling?
I don't think it's correct even. Does AI really? I think it spells really nicely. It's just more that it sounds...
That makes no sense.
Sounds like the same answer every time, so somehow it didn't seem creative enough. In fact, I can't easily spot. I cannot easily spot AI. All I can say is this sounds very reasonable. Oh wait, that's completely wrong. Well, wait, you're a good liar. And, and that's at least how I look at the AI. Was that oh, sounds really reasonable. More like an excellent student, a student who is an excellent BSer. It's and can spell and all that. Absolutely.
Thank you.
All right, one final question. We're almost at the end of our time. What do we know about the energy consumption needed for quantum computing, how it compares to standard computing, and how likely it is to evolve or become more efficient over time?
Yeah, that's a good question. I mean, this is another thing that one is estimating, and my understanding is that it's actually very energy efficient, so that's good. Of course, that's set in isolation. How much energy do you need to do the computation? And then there was the fridge and whatnot, and that doesn't count. So, so that way I don't know how it really works in a realistic estimate, but I know that the actual operations that are needed, rather few. And that sounds to me like something at least one could theoretically speaking claim is very efficient. But I don't know
So
if
it would
that's
scale, basically.
What?
It would scale per computation. Once
It
you
would
have a
scale,
facility
something like that,
that's,
yeah.
then doing more computations on
And
an
that
existing
seems to me it should be quite good. But I don't know if that's fair. I'm a little unsure if that's overselling the situation.
Oh, okay. One final question in the room.
So qubits aren't exactly 0 or 1, right? But how do you input stuff into a qubit? How do you tell it to go into?
No, you actually start them as exactly that. They are zeros or ones. That's how you put them in. Then when you start manipulating them, you kind of turn them so they're equally much 0 and 1. Then you try to do a logical operation where depending on what one qubit was, it should flip the other or not, and so on. And that quite quickly, after just a few operations, bring up, oh, the whole network is actually no longer can you identify what is this one without telling, oh, but it's related to all the other ones are. And therefore, if you just look at one, it's really, it's 50-50, 0-1 or some such thing, but that tells you nothing. It's all in the correlations with the others.
All right, we're at the end of our time, so let's thank Professor Finn Larsen again.